I want to graph the function f of x equals 6x minus x cubed minus x to the fifth. I'm told to first use the leading coefficient test to determine the end behavior. I'm then asked to find all of the zeros and their multiplicities. I'm supposed to list the x-intercepts, find the y-intercept, determine if the function is even, odd, or neither, because that will connect it to a symmetry relationship if it has one that might help me graph it. And then finally, I'm going to graph the function using all of these things, plotting other points as I feel like I need them. All right, the leading coefficient test asks me to know the degree and the leading coefficient. The first thing I'm going to do is rewrite my function. I always like writing the thing with the highest power first. Speaking of which, the term with the highest degree tells me the degree of the polynomial. So the degree is 5, and the leading coefficient is -1. And of course, what's really important there is the leading coefficient is less than 0. A function with odd degree has an end behavior that is either going up all the way or down all the way. Because my leading coefficient is negative, I know it's this one. So this is a little picture I like to draw for end behavior. If we wanted to write it in words, we'd imagine that we were a person standing right here, right in the middle. And as we looked, we'd say, well, it rises to the left and falls to the right. I kind of prefer thinking about going in the increasing order of x, and I'm always going down on the end behavior. It might, bounce around in the middle, and that's why I used some dots there. But on this side of it, right on the far left, it rises, and on the far right, it falls. It does a pretty good job of describing the end behavior. Now my job is to find all of the zeros and their multiplicity. So I think I need to factor this. And the first step to factoring anything is to pull out the greatest common factor, which would be an x. And because my leading coefficient is a -1, I'm going to go and pull out a minus x. Okay, so now that I've pulled out that minus x, I see something that's in a quadratic form here, so I'm going to keep factoring. I'll need an x squared times an x squared to give me that x to the fourth. Looking at the last term here, I know I'm going to have things that multiply together to give me 6, but have a difference of +1. So I think I'm going to have a +3 and a -2. Now if I imagine setting all three pieces with a variable equal to 0, I'll find out the zeros are x equals 0. Here I would have x squared equals 2, so I'd get x equals plus or minus the square root of 2. And here I'd have x squared plus 3 equals 0. And because I was asked for zeros, not x-intercepts, and I was asked to find all of them, I need to report the complex ones. So if I take 3 away from both sides, get x squared equals -3, I'll get roots that are complex. I'll get plus or minus I times the square root of 3, right? Because I'll get plus or minus the square root of -3, and I can bring the I out front. All right, so I have, let's see, 1, 2, 3, 4, 5 zeros in total. I'm supposed to report their multiplicities. This is to the first power. If I imagine factoring this into an x minus root 2 and an x plus root 2, those will all have multiplicity 1. And this comes from the same kind of term as this, so also will have multiplicity 1. So I want to write down my zeros in a chart. So each zero is going to get a spot in the chart. And they all had a multiplicity of 1. And one neat thing about working with polynomials is if we find all of the multiplicities, we add them all together, we'll get back to the degree. 1 plus 1 plus 1 plus 1 plus 1 is 5, and we've gotten back to the degree. All right, so next thing I was asked is to write down the x-intercepts. Well, those come from my real zeros. After I was asked to write down my x-intercepts, I was asked to write down my y-intercept. And I could imagine plugging 0 into the function, but because 0, 0 is already on my list of intercepts, it has to be the y-intercept. It's the lone point that can be both kinds of intercepts. Finally, we're asked to determine if the function is even or odd. So here's my original function, after I've rewritten it anyway. And what I'm going to do is go on and replace x with minus x and use that algebraic test. Well, I'm raising a minus x to an odd power in each case. The minus will come out front. All of the signs are going to change, and this is the opposite of what I started with. F of x is an odd function. So whatever I'm getting ready to graph has to have that symmetry about the origin, that rotational symmetry. All right, so let's take what we've said so far and try to start a graph of the function. We know the end behavior rises left and falls right. We've written down all of our zeros, which become our x-intercepts. We have a y-intercept, and we know our function's odd. I'm going to plot some additional points here in a moment, but I want to go on and start the picture based on what I have here. So I'm just going to count by ones. So I need to plot points at minus root 2 and positive root 2 on the x-axis and at the origin. The square root of 2 is about 1.414, so about here and about here. And these dots are big enough that assuredly the square root of 2 is somewhere in there. And I know that from this point it's supposed to be falling to that point, right? It rises left, and then from this point I'll be going downwards. I'm going to plot some points, so I'm not going to graph that in yet. Because all of my multiplicities on my x-intercepts are odd, I know I'm going to go through, so I think my function's going to have a shape that comes through and hits an intercept and then waves around like this with the origin right in the middle, giving me that nice odd shape. I just want some idea of how high and how low to plot those points. So I'm just going to pick some values of x to plug in a table, to plug into the function, and help me plot these points. So I'm going to plot points at minus 2, minus 1, 1, and 2, where I'm kind of giving myself one thing in between and outside of all of my intercepts. And you can pause the video here, plug these values of x into the function, and see what happens. So, when you plug minus 2 and you get 28, if you were to plug 2 and you get minus 28, and I know that because it's an odd function. You plug in the opposite of x, you get the opposite of y. You plug in a minus 1, you get out a minus 4, and if you plugged in a 1, you'd get out a positive 4. Okay, so I'm not going to plot these points all the way up at 28, right? Because my board's not going to go that high, but it lets me know that this part's very steep. And so is this part. At 1 and minus 1, I can plot those points. So I know my function goes through these points. What I don't know for sure is I don't know whether those are minimums or maximums, right? It might go a little bit past that and turn. And I don't know, but I'm just going to go a little bit past and then turn around just to emphasize the point that I don't know whether that's the highest point, excuse me, the lowest point or the highest point. You'll actually learn how to do that in a calculus course. But what I have here is a function that's definitely odd. You can rotate it around the origin, it looks the same, and it meets all of the criteria I've written down over here.